We have a special presentation today. This is with an 18-minute clock on it. And Mike, can you start doing your transition? Yeah, walking. Many of you know Mike. Mike will introduce some of his history in his presentation, but Mike and others have been complaining that this Congress on the Future of Engineering Software hasn't talked so much about the future. I don't necessarily agree, but I heard of a presentation that he gave in Europe to a university, and I saw the presentation, and I thought I would throw some gasoline on the fire to spark our conversation on the bus, and I'd like to introduce to you Mike Payne.
Thank you, Brad.
Set the clock.
As Brad said, I'm going to talk about something completely different, the future of mechanical CAD. First of all, I should tell you that it was in Paris in a university, and good news is this presentation is in English. The good news is that it's about half the length, and the bad news, I'm standing between you and stargazing, which means there probably won't be time for embarrassing questions that I don't know the answer to. So first of all, before we talk about the future, we have to understand the past and the present. As somebody said, what is past is prologue. Because if everything's fine, then the future is more of the same. So we start with something very simple, which is a process in general that people go through. You have a fellow mechanical engineer or team that designs some widget. There's a lot of widgets designed. Maybe they're screws. And when they believe they have it done, they give it to the person who makes the production model, drawings, call it what you will. When he brings it back and says, is this what you want? And they go around the loop again until it's done. And that's where the production drawings or model reside. Then they release it. And then the accelerator pedal sticks, and they need to have an ECO, and they go around the loop again. And that was how things used to be done, and in practice, a lot of them are done that way still. And everything started as 2D drafting. The first mechanical CAD was 2D drawings, and it was around the late 1960s, which some of us remember. Is that me making banging noises? Okay. And AutoCAD appeared at about the same time as the PCAT. At that time and today, the CAD output of that is paper, plots, which were equivalent to what you got from a draftsman. And as some companies still have it, that's the legal document for subcontracting and the rest of it. So we shouldn't forget that. And we still have 2D. Why? Because it always works. There's no question that. But we've got lines and arcs and dimensions, and they're always there. You can transfer the data between programs. It's simple. And it's state-based. You don't have to know who or how the drawing was created. The fundamental storage in 2D is geometry, and annotation, notes, dimensions. And if the software version changes, the drawing doesn't. The line is that long. So there was the challenge of evolving to 3D, and the computers got faster, so we could do more things with them. And why? Of course we want 3D. It's less ambiguous. So the early 3D was very primitive. One of the first ones I remember was link lines in Medusa. Does anybody remember that? Oh, they're as old as I am. Then we had wireframe, which was an extent of, call it 3D drafting, and visualization. And you could create but not change solids, which is show the boss something. But as building this presentation, it's an iterative process, design. Writing a letter is an iterative process. Designing anything's an interactive process. Refine it until you're satisfied. And so in 3D, as you've seen, there's been an evolution, and each generation overcame the perceived limitations of the previous generation. So there's really no such thing as the status quo. Keep doing what we're doing, and it will continue to evolve. And the challenge Brad, of course, has given me to look at, in a sense, is will my predictions come true in 10 years when you look back? So in 3D, there's really two generations, basically, which one was state-based. The 3D wireframe, it was kind of like 2D. It was state-based. Surface modeling is that way. And history-based solid modeling, which took two fundamental forms, constructive solid geometry and feature-based modeling. And to save words and make it bigger type for the visually impaired like me, I just abbreviated that. And there's other things that came along like functional modeling and direct editing. Many of the analysts like to talk about history, so I'd like to say a few words about that. History is not the same thing as feature-based parametric modeling. Many types of systems have history. History means you know how you built it, and it relies on that. Constructive solid geometry, by the very name of it, has history. It's just different from feature-based modeling. And often direct modeling systems, and we all know some of them, are referred to as history-free, but they're not necessarily history-free. To be history-free, the software must not know how the model was built. It's nice if it did, but it doesn't have to. You give it a chunk of geometry and you can work with it. And you'll be able to change the model in any way the user wants. Customers just want to get their job done, so they don't really care whether you call it history or not history. That's kind of like having ACIS parasolid wars. That was really rather pointless. Feature-based modeling. The first attempt, we all know, was ProEngineer. And the breakthrough was to make models that you could change. And the original slides about ProEngineer said it was Lotus 123 for engineers, and hence the name ProEngineer. And in the end, the people who use it today are the CAD professionals, not the engineers, as we'll talk about in a bit. That's if my clock doesn't run out. And it's the basis of most systems that are out there today. In 1988, we had 1 MIP computers, and we thought we'd done wonderfully. We could make 10 feet. But they were simple. We thought it was spectacular. Is that me here or there?
Let's just use this one.
Oh, it's bad? Oh, okay. So in feature-based modeling, the data is now different from the 2D case. The instructions of the features are the recipe, and they're executed sequentially. So the data is the instructions, their sequence, and sometimes sketches. And theoretically, you don't need anything else. You regenerate the model, and you get geometry, picture, and I can't move or the sound goes down. The drawings are generated as views of a model. And it's clearly very widely used. But most of the people who use it are highly skilled, trained professionals. They're highly valued, meaning they're highly paid, and they're rather than degreed engineers. One of the industry watchers was complaining that only 5% of the people who operate CAD systems in the US have college degrees. I think that's great, because it says engineers do engineering. Now, it's been coupled with various forms of product data management, and so they combine it and they call it product life cycle management. And the beauty of it is it's really hard to interoperate between competing systems, having the modeler from one system and the data management from another. And so it's hard to incorporate the best-of-breed specialized tools from several vendors, as you would in many other industries. Feature-based modeling plus PDM, is that really PLM? And it tends to lock customers into buying everything from one vendor. And I believe that best-of-breed integration in PLM is just a dream. So is there a problem? If there's no problem, why would anybody change? There are these people who are still using 2D, And more people use 2D than feature-based modeling. Engineers do not sit at a CAD station 8 hours a day and do modeling. But you need extensive training. And by the way, engineers don't use Word for 8 hours a day either. So if there's a problem, it's that there are fundamental limitations of the current approach which will not be overcome by enhanced versions of these tools. And they become harder and harder to use as more capabilities have been added. And the fundamental principles are not that easy to learn, and the products are not intuitively obvious. Here's a list, and I'll discuss them briefly, of the limitations that exist, as I see it, in feature-based modeling. Version sensitivity, assembly relations, management of change, and the order and parameterization of features. The correct regeneration of geometry between software versions requires that the recipe, how it is interpreted, is the same, and that there is no change in a geometry engine that would result in different geometry or topology. If that is the case, a current step being processed or a later one can fail. And all systems exhibit some failure rate when going from one version of the software to another. And that's somewhere less than 1%, say between 1/4 and 0.5%. The larger the assembly, the worse the problem. Now, there's a more insidious problem, which is it doesn't appear to fail, but it changed. The model regenerated, no errors, but the geometry is slightly different, or the topology is slightly different, or the mass properties are different. So one vendor improved his calculation of mass properties, but it resulted in a change of the previously determined values when that assembly was brought into a new version. And that was an improvement, of course, because now was the right answer. In large assemblies, there's often very complex relationships between component parts and sub-assemblies. And changes made after release of one component can have unintended consequences for others, especially when the term assembly features are used. And so a lot of companies actually flatten their model when they release it to avoid those problems, and then they lose all the hierarchy, so that only one component can be changed. The complex relationship between elements in assembly is partially caused by the lack of sophistication on the part of the data management systems. In most, there's no real differentiation between minor cosmetic changes and substantial changes. So if a part's changed, you have to change every assembly that uses it, or maybe many. So there was a case of a submarine where they changed an elbow from copper to brass, and you regenerated a submarine. And you can say you can do it in instant time, but what if it didn't regenerate? Cascading dependencies. Each feature depends on a previous one, and it gets more, or a set of them, and it becomes more and more complex to understand how it was built and the programming that created it. And a viable change means that you can change the model by one or more of the parameters that exist, and sometimes you can't, so you rebuild the model. So, this is not all bad. There's about 1 million seats of feature-based modeling. Big aeroplane was designed with it, another big aeroplane. That's a pretty complicated assembly. Most cars were designed with it. Most consumer products. And a lot of people like their tools. But there's 4 million seats of mechanical CAD. And for somebody who wants to argue with that number, those are the ones that were paid for. But there's a lot of potential users who have not bought 3D systems for one reason or another. Other speakers have talked about, other sophistications of 3D and toys that people get, games that people play with have more sophistication in 3D than we're offering to engineers. And as they come out of school, they will expect things that we're not providing them. The PLM value proposition really doesn't exist until the design is done. And it's a production system. And you could argue it's some of the functions of an ERP. I won't talk a lot about that. I think you can all read that. But a key point about PLM, most do not understand that there's more than one BOM, material takeoff, for a big design. And it all depends on who you are, what you're looking at, whether it's a part or an assembly. Whether you're the subcontractor, it's an assembly. When you're the OEM, it's a part. And so there's a set of interrelated BOMs, and I don't know any system that will really accommodate that. So the future. The feature-based modeling has its value, but the future is something else. And the 3D tools in the future must address the unmet needs of potential users. So I'm not going to give you a list of this is what people will do, but some guidelines on what I think they will have to have. Is direct modeling the next step? Not as it is today. It needs to be expanded. Could open source be it? No. It's too complicated. And can it be marketed as a pay-as-you-go? Yes. So the target would be that all the people have involved in engineering, design, production of physical objects will want to use 3D. Not be forced to use 3D, but want to use 3D. And the tools have got to be much easier to learn and use because we're all lazy and we don't like going to class. And we don't want to pay for it. So a casual user must be able to perform, like I do in PowerPoint, basic functions in a discoverable manner without training. In other words, it's discoverable how to do this. Once a model's been created and released, it can't change due to the software. In short, intelligence must be built into the software. Tools have to understand what's being attempted and provide assistance. Should be able to reuse data from any system. We cry over the years about interoperability, but why can't we have it? The best-in-breed tools need to be interchangeable, just as they are in other industries. And I believe that the fundamental storage must be geometry and topology and not a recipe. And so it must be interchangeable. And in general, it has to have lower cost to broaden the reach. So in short and simple terms, everyone should want to do their work in 3D, make it discover, have intelligence built in, reuse data, interchangeability, inexpensive, and long-term storage that it really is long-term, and that means it can't be binary. It has to be in a form like PDF or STEP, but it can't, or like DXF, but it can't be somebody's binary format that will change when the computers change. So Joy's law, I seem to remember, is that innovation will happen. It just won't be here. And I think we've heard some indications of that. It's not likely to come from a current player unless they change their behavior. The existing companies who sell and service it don't like new technology that threatens to kill their own children. So opportunities for new companies to create the products of the future are in fact limited in this industry by the sunk cost, the investment, money, and time in existing products by vendor and customer. But customers always seem to find a way. So, for you to argue with me about or talk about is what's the solution, who will deliver it, and what's the business model. Thank you.